Hi, students. I just wanted to provide you with a reading of the STEMScopedia. It can be helpful to you all as you are trying to read this 5-page document here on my screen, and it'll help get you through the reading a lot faster. So here goes. Our world is full of diverse elements, mixtures, and compounds we call matter. Look at the picture of the ice cream sundae on the right. How many different types of matter do you see? All matter is made of atoms or molecules that are affected by heat. Why is this ice cream sundae melting? If you heat matter, such as the sundae, then you are adding thermal energy, which makes the atoms and molecules move faster. When they move faster, the average kinetic energy of the sundae will increase and cause the temperature to rise. If the sundae gets too warm before it is all eaten, it will melt. It will change from a somewhat solid state to a liquid state. So let's look at this sundae. Underneath the picture of the sundae is the vocabulary term matter. Matter is anything that has mass and takes up space. Let's look at heat. Heat is energy transferred between two objects of different temperatures. Energy will continue to move in a predictable pattern from a warmer site to a cooler site until all sites have reached the same temperature. Thermal energy is the total kinetic motion and potential energy of tiny particles that make up matter. The faster the particles move, the warmer the matter becomes. The next section, adding or removing thermal energy. Thermal energy can be transferred from one object or system to another in the form of heat. Depending on the physical properties and temperatures, all matter can exist in 3 states or phases: solid, liquid, and gas. All forms of matter have specific temperatures at which they melt, freeze, condense, or vaporize, which are part of their physical properties. When matter changes state, it is a physical change. Adding or removing heat from matter is what causes particle motion, a form of kinetic energy, to increase or decrease, temperatures to rise or fall, and states of matter of a pure substance to change. So let's study the diagram real quick, shall we? Here's a cloud or water vapor, which is a gas. Here's liquid water. Here's the solid, water as ice. And I want you to look at the spacing in between the particles of matter in each one of these different states of matter. In the gas, they're spread far apart. In the liquid, they're close together. And in a solid, they're tightly compacted together. And I want you to look at this temperature gauge. Kinetic energy and temperature increases, so does particle motion and pressure. So as I go from the coldest temperature to the highest temperature, look at the particles, they start spreading out. The temperature increases, so does the kinetic energy. So particles in a solid move really, really slow, so slow that you can't see it. Think about the chair that you're sitting on. Yeah, the particles of matter are moving. Why don't you notice it? Because it's at a temperature and it's that's so low that causes those particles to be jam-packed closely together, and they're vibrating very, very slowly against each other, having the lowest kinetic energy out of all 3 states of matter. The liquid has a slightly higher kinetic energy than the solid. And then the gas, those particles have the highest number or level of kinetic energy. So that's why the arrow here is going up. The particle motion even increases, and so does the pressure. Think about this. The volume of a solid is fixed, right? It's going to take up the same amount of space. It doesn't spread out all over the container. But the particles in a gas, they actually spread out, which causes those particles to press up against the sides of a container, increasing the amount of pressure. This is why you can't puncture a can of spray starch or a can of Lysol. It's very dangerous to do that because the content is under high, high pressure. All right. Let's move on to page 2, heat and matter continued. As heat is added or removed, the state of matter can change. Let's read about solids. Solids are a state of matter in which all particles are tightly packed and move very little, vibrating particles in fixed positions. Liquids, the state of matter in which particles are free to flow over each other and take the shape of their container, freely moving particles in loose contact with other particles. Gas, the state of matter in which particles are spread apart and are moving quickly. They can exit an open container. Gas particles are freely moving particles that are not in contact with each other, except during collisions. They collide and bump off of each other. Now, what do you think? What do you do when your cup of cocoa is too hot to safely drink? If you let it sit for a few minutes, it'll cool off. The longer it sits, the cooler it will become. Wait a minute. Why does the cocoa get cooler from its surrounding environment while the ice gets warmer from its environment? Does warmth flow into the ice and the coolness flow into the cocoa? I wonder what's happening here. So, to understand what is happening, you should know that heat is the transfer of thermal energy. And heat, listen to this is very important. And heat always flows from warmer areas to cooler areas. When two areas reach the same temperature or average thermal energy, the flow of energy stops. Therefore, heat moves from the air into the ice, causing it to melt. Also, heat moves out from the hot cocoa into the surrounding cooler air. So let's study the picture here. In this picture, I see like the steam coming off of the hot cocoa. It's cooling as heat flows from it to the surrounding air. So heat is leaving the cocoa into the surrounding air. Whereas when you have that glass of ice, the heat from the surrounding air comes into the ice, causing the ice to melt and become cool, become warmer. Look out. Have you ever heard someone say, "Shut the door, you're letting the cold air out or the cold out"? Have you ever been told not to stand in front of the refrigerator with its door open because you can let out the cold air? I know I have. These statements are incorrect because heat always travels from areas with higher thermal energy to areas with lower thermal energy. Therefore, you can let the heat out of the door in the winter, but you are letting the heat in the door in the summer. Page 3, heat and matter continued. The transfer of thermal energy from one substance to another involves movement from areas of higher or warmer temperatures to areas of lower or cooler temperatures. The transfer or heat flow continues until the temperature is the same. This energy balancing act is called thermal equilibrium. In the word equilibrium, I hear the word equal. So, what heat wants to do, it wants to flow from where it's really hot to where it's cold until the system reaches the same temperature, right? So, let's imagine this block of cold is 0 degrees Celsius. We know that's freezing. And this block of hot is about 100 degrees Celsius. Let's look what happens. The heat flows from where it's hot to where it's cold until they reach thermal equilibrium, and then both blocks become 50 degrees Celsius. You see how that works? They've reached equilibrium. So now let's look and see what we can apply this to from a real world example. You guys are familiar with the water cycle, right? You learned about that in earth science. How heat affects the water cycle. Let's take a look. Heat causes ice to melt and flow downhill. Remember, we talked about glaciers and ice caps? Look at this. Heat from the sun, which is our major thermal energy source on Earth, causes this ice on the top of the mountain to melt, become water, and flow downhill. Now, let's look at what's happening in this cloud. The cooled water vapor in the cloud condenses into water droplets to form clouds. When that cloud gets so heavy that it can no longer hold the vapor, we get precipitation. So when rain falls through cold air, it loses heat. And guess what? It freezes over time. And that's how we get hail, sleet, and snow. Energy from the sun is added to Earth and its atmosphere. We knew that. Heat at the surface helps water to evaporate. So when the ground gets hot and when the surface of water gets hot, it evaporates, moves up into the air, and becomes clouds. Clouds get heavy and becomes precipitation. And let's just look. It's a cycle, meaning that this happens over and over and over again. And lastly, heat flows from the rising water vapor, causing it to cool and condense. And that's how we get clouds. Okay. Page 4. Look out. Total thermal energy versus temperature. Let's see how these two things or ideas are related to each other, thermal energy and temperature. How would you measure the total thermal energy of a pure substance? If you were thinking you would take the temperature of the substance, you would only be partially correct, right? Temperature is not a direct measurement of the total thermal energy of a system. When you take the temperature of a substance, you are really measuring only the average kinetic energy of its particles. You also have to consider all the atoms in the material as well as its conductivity. The total thermal energy of a substance depends on 3 factors, guys: temperature, the total number of atoms or molecules in the system, and conductivity. In other words, temperature would be the average kinetic energy of the particles in a substance, whereas the total thermal energy would be the total kinetic energy of all of its particles. So let's kind of break that down. So temperature would be the average kinetic energy of the particles in a substance. So remember, we talked about kinetic energy in the previous unit being the energy of motion, right? So the hotter a substance is, or the more heat we apply to a substance, causes the kinetic energy to increase. That's why gas particles have the highest level of kinetic energy versus a solid. So when I'm talking about total thermal energy, I'm talking about the total kinetic energy of all of the particles. So it's when you take and consider all of the kinetic energy in a particular substance or system, then you're talking about the total thermal energy. I hope that helped. So what do you think? Which one has more total thermal energy? A glass of water or a pool? And let's revisit. Total thermal energy is the total kinetic energy of all of its particles when we're talking about a substance. So which one has more? The glass of water or the water in this pool? Two different substances can have the same temperature, but the more massive, meaning larger, the object is, that object will have more total thermal energy because it has more particles. Therefore, the pool will have more total thermal energy than the glass of water, as the pool has more molecules in motion, right? You have millions, billions of water molecules in a pool versus those in a glass. Therefore, you have more kinetic energy. Does that make sense? If you have more kinetic energy, then you have more total thermal energy. Now, we are going to prepare for our heat and matter task. You're going to look at this glass of soda and then use your knowledge about thermal energy transfer, things going from where it's hot and traveling to where it's cooler until the system reaches equilibrium. So use your knowledge of thermal energy transfer to explain how heat is affecting the following things. Let's look at it: the ice, the soda, the glass, and the surrounding air. So we're getting ready to use our graphic organizer. You'll be provided with a rubric and a word bank in order to answer this question.